Okay, so as I was saying, this is week 6. So in week 7, I'll post the guidelines for MRI project. That presentation will be slightly different from what we did for the CT presentation, in the sense that all the presentations will be done in one session here during the final exam period. Okay. And so the idea is I'll post that probably Monday of next week, and then you'll have about a week to sort of pick a project, form your groups. The idea is before we leave for the Thanksgiving holiday, we'll have the groups and everything all figured out. Okay, and then that will still give you, I guess, about 2 or 3 weeks to sort of do your projects. All right, any questions on that? Okay, if not, why don't we get started on the topic for today, which is, okay, good, that still shows okay. So we're going to pick up where we left off in terms of the MRI concepts. And we're going to review a little bit about encoding with gradients. We're then going to work towards the MRI signal equation. And hopefully we'll get to K-space trajectories and pulse sequences. So pulse sequences are really the heart of MRI. This is the software that controls the entire system. And so we'll talk a little bit about what pulse sequences do and how they are used to implement K-space trajectories. And so hopefully by the end of today, we'll go through sort of the basic bread and butter imaging that you would see on pretty much every system in the world today. So right now, thousands of scans are being done, and we're going to work up to what's called the spin warp pulse sequence, which is sort of the bread and butter sequence that most MRI systems use. So just to remind you, remember the 4 stages are the magnet creates this polarization. That's how much magnetization there is. The RF coil does the excitation. So that was one of the pre-lecture quiz questions. So I think most people got that right. So the RF coil transmits a pulse or a train of pulses, and the job of those pulses is to excite the magnetization. The gradient coils do encoding, and so we'll spend more time on that today. And then also the RF coil on the receive side, they do integration. Okay, but when they're receiving, they're not sending any pulses in. They're just in a passive mode, listening to what's happening. So just to remind you what gradient fields is that we use these linear gradient fields to create linear variations in the magnetic field, such that get this mouse working. Sorry, this doesn't be working. There we go. Okay, such that if we have a spin here at the isocenter, remember the isocenter is where we assume there's no delta B is equal to 0. So we're always, at isocenter, we're always assuming the field is B sub 0. So the spins will recess at gamma times B naught. If we go here, since it's a linear gradient, this just means that the field here is stronger and the field here is weaker. And so these spins will process faster than these spins here. Now, there was one of the pre-lecture questions was asking about, what do gradients do? And most people got the fact that what they're doing right now is obviously imposing spatial variations in the frequency and phase, okay? But a number of people did say that it imposed variations in spin polarization. And that may be a trick question, because you might think polarization has to do with maybe the phasors or something like that. But that's not the way we use polarization in this course. Polarization really refers to how much magnetization there is, okay, available. And so the polarization is due to the main field B0. It's not governed by the gradients. Okay. So this is a problem from the book, and we're just going to work through this just to give you a better sense of how the theory and how these things actually play out in practice. So the question is as follows. We have a non-uniform magnetic field pointing in the Z direction, and the B field varies as a function of Z. B of Z equals 1 plus 0.5 Z. Okay, so it's going to be a linearly varying field. the magnetization processes around the z-axis. Suppose at time t equals 0, all the magnetization vectors have the same phase. All right. So essentially, the main assumption you can make is when you excite the magnetization, all the magnetization is in the same phase because they've all experienced the same excitation if things are uniform, and so they're all in the same phase orientation. But now they're going to get out of phase because they're in the presence of a gradient. All right. So the question is, at what time will the magnetization vector at z equals 1 centimeter and z equals 0 have the same phase again? So this is exactly problem 12.1 from Prince and Links. And then you can say, using the time that you calculate, what will the phases be at z equals 0.25, 0.5, and 0.75 centimeters? For this problem, you're asked to assume that gamma over 2 pi is 4257 hertz per Gauss, or 42.57 megahertz per Tesla. All right. So let's take a look at this problem. So essentially the problem is this. We basically, we'll just draw the z in this direction here. So at 0 and at 1 centimeter, right? We want to look at the spins. So basically, at time equals 0, they're aligned. Okay. But we're in this presence of this B field, right? Like this. Oh, sorry. Erase that. So the gradient in the B field is such that it's at 0 here, right? And it's going to linearly increase. So this is the 1 plus 0.5 z. Okay. So we know that the B field at 1 centimeter, right, is just going to be 1. And we'll assume everything here is in Tesla. 1 plus 0.5 z. Okay. Oops. And here it's, yeah, I guess the units don't quite work out here because the 0.5 times z still has units. So let's just assume that that's, we can just, that's like 0.5 is like Tesla per centimeter. Okay. So that B at 1 centimeter equals 1.5 Tesla. Okay. That's a pretty big gradient. Okay. No, that's much stronger gradient than we have in any of our systems. All right. So the important thing is that we don't really care what the actual absolute magnitude of that field is, but we care about the difference between the field of those two spins. So the delta B, right, at 1 centimeter is equal to half a Tesla. Okay. So now we can say, well, so reference to the spin at 0, what's the frequency? What's the delta F of the spin at 1 centimeter? And so it's going to be gamma over 2 pi times delta B at 1 centimeter. Okay. So that's just going to be, we'll use the thing that's in megahertz per Tesla because we're in units of Tesla here. That's 42.57 megahertz per Tesla times 0.5 Tesla. So that's around what, 21 megahertz? So that means that this spin here at 1 centimeter, reference to this spin here at 0 centimeters, is spinning 21 megahertz per second faster. Okay, that's the relative frequency that is what really matters, right? So then the question is, how long is it going to take for that spin to, it's going to get out of phase, and then at some point it's going to come back in phase, right? Because it's this spin here at t equals 0, we can just assume it's stationary because it's the reference spin. And so we're saying this other spin at 1 centimeter is you're going to start processing faster. And so how long is it going to take for it to get back to pi equals theta equals 0? So you know that delta F is 21 megahertz. So what would be the period required for it to get back to theta equals 0? Any ideas? Okay. So in general, what's the relationship between frequency and period? Yeah, right. So we could just say that the period is just going to be 1 over the delta F. All right. And so that's shown here. We did this exact calculation. Delta F here is 21. And so 1 cycle is just going to be 1 over delta F. Is going to be 0.047 microseconds. Okay, so it's a pretty short amount of time. So what we find is that basically, if we draw this problem out, you know, if we wait that amount of time, this spin here and this spin here will be aligned again. Okay. And then the question goes on and asks what's happening at 0.5, 0.25, and 0.75, right? And you can plug in and figure out what the phase is, and then you can calculate it. But you can also just think about, well, if I only went half as far, then the frequency is only half as much. So I'm going to only acquire half the phase. So you just write down the answer like that, right? Okay. And if I went to 0.25, the frequency is only 1/4 as much delta F. And so, and since the precession is clockwise, it means I'm only going to go 90 degrees clockwise, right? So it's this, and then so on and so forth, and you can write this. Okay. So essentially, that's sort of this is a pattern you're going to see a lot of the problems where basically you're sort of asked to visualize what the phasors are doing and how are they oriented as a function of space. So this is typically what you'll see is basically, if you have a uniform gradient on for a certain amount of time, you're going to just see the phasors wrap around, okay, and then they'll repeat at some cycle. So you'll be sort of, when you look at these diagrams, you'll say, okay, what's the period at which this pattern is repeating, and which way is it going? Is it going clockwise or is it going counterclockwise? And that will give you what you need to know. All right. Okay, so let's review a little bit of K-space, because K-space is talked about all the time in MR. So remember, K-space is just the notation we mean to represent the Fourier domain, okay, the data in the Fourier domain. So as we talked about last time, different parts in K-space represent how much of the image is represented by a certain spatial frequency. So if the Fourier transform is really dark here, right, that means there's very little of my image that's represented by a frequency component out here. So most of my image can be represented by frequency components here, where it's fairly bright, right? And there's relatively little contribution from these outer parts of K-space. And remember, if we're along the Kx axis, okay, these correspond to spatial components that go left to right or vary along the x direction. If we're along the Ky axis, that corresponds to spatial components that vary up, down, and that's along the y-axis. And if we're off at a diagonal, then those correspond to diagonal variations, right? So just to remind you, if you're at some random location in K-space, okay, you can just use the Pythagorean theorem to realize that the magnitude of your K vector is just square root of Kx squared plus Ky squared. And if you take 1 over that, that gives you your spatial period. And the angle that you're at is the arctangent of Ky Kx. Right? So just remember, if I give you a point out here in K-space, right, an easy thing to remember is, if I imagine drawing the vector out to that, then the spatial variations are going to be perpendicular. In image space, that represents spatial variations that are perpendicular to that K vector. Right? So that's sort of an easy thing to remember. Okay, so I think hopefully this movie will work. So what you're going to see here is basically a movie where we have the Fourier transform or K-space representation here, and we're going to start incorporating more and more data here, and then we're going to sort of see what the image looks like as we incorporate more and more data. Okay. So you can sort of see we've got most of the image there, and now everything else is just adding finer and finer detail. Yeah, question.
This is there's the Fourier system frequencies of all the plane waves reconstructed in it, right?
Yeah. So right. So basically, when we're at the beginning of our thing, we only have very low frequency plane waves, right? But that's sufficient to sort of describe the overall shape. Okay. We get a little more. Now you're starting to sort of see, okay, you can tell it's a person now, right? And you're starting to fill in some of you sort of tell it's a person. You can sort of see the brain. You can sort of see the nose. Sort of see where the brainstem might be. You can sort of see the skull. But you would not want a doctor to diagnose you based on this image, right? So you've got to get more detail. Well, so now you're starting to see better, but there's a lot of artifacts here, right? And there's just still not, you wouldn't really want a diagnosis based on this image. Now it's getting a little better, right? You can start seeing the sulci here. You see the corpus callosum, you see the brainstem, you see the cerebellum, so you even see the tongue here. Here's the nose, the sinuses, okay, the spine, some muscles, fat, skull, skin, all right? And now on this display, it's pretty hard to see, but we are filling in finer and finer detail. Right? But the basic idea you want to keep apart is this is what's captured by the inner part of K-space, very low resolution. And so when we go talk about resolution, there's a trade-off. To get better resolution, we have to acquire more and more data in K-space. Right? So when we go to sort of designing sequences, we'll come back to this when we look at, given a certain resolution, what do you need to do in K-space? So here's some examples. There's more examples in the supplementary video, so you can always look at that. But the idea is here's the image, and here's the K-space representation. If I look at this, what I've done here is I've zeroed out all these contributions in K-space. Okay. So in particular, I don't have anything along the K-axis, right? So I'm really going to lose these strong variations in the X direction, right? So imagine if you look at, for example, this edge here is pretty sharp in this image, right? Because that's a variation going left to right. If you look at that same edge here, oh, sorry, you can sort of see it's blurred out a little bit because I've lost that part, that plane wave that would represent that edge. And you can also, these are what are known as Corduroy artifacts, which you see once in a while in MR. So if you ever get an image back that looks like this, then you'll sort of understand what's going on. These happen anytime, basically, the energy we're looking at in MR is at the sort of RF frequencies. And so if there's a leak in the shield around the room, some energy can get in, or it could be even, this happens a lot, the systems tend to vibrate, and we'll talk about that in a minute, but sometimes even just little metal pieces hitting each other once in a while can cause a spark. And so what happens is you're going through Fourier space, once in a while, you might get just some spurious energy that just pops into your acquisition, okay? And so the idea is if that happened, let's say I got some spurious energy here, then this is what the image would look like, okay? And we can sort of convince ourselves that makes sense, because if I go from the center K-space and draw the line out there, and I draw the perpendicular to that line, then that is telling me, I have these vertical stripes, right? Or these stripes in this direction. Similarly, if the energy occurs here, then I go out here in K-space, and then I know that it's going to have stripes like that. All right. So basically, if you get an image like that, you can just look at the stripes and the pattern. You can say, well, actually, I know where in K-space that artifact occurred, right? Just by looking at the image. So just to recap, a lot of times we'll draw things like this, spatial variations, right? And so this corresponds to a place in K-space like that, just simply because, we can sort of use our little sort of mnemonic and draw perpendiculars to that. But we're going to also want to start thinking about things in terms of spin, phase, okay? Because really underlying is we don't have this in MR. What we have is this. We control the phase of the spins, right? And so the idea here is that, this, you can sort of see that this has a diagonal spatial pattern, right? I mean, there's sort of this organization of it in this diagonal pattern. It's not the same frequency as this, but it's sort of, but we'll see things like this later in the lecture that we're going to be looking at sort of spatial patterns in the phasor orientations. Yeah, question.
they're all the same slope, maybe a couple of
Yeah, if I remember what isoclines meant, then maybe, but I don't remember the exact definition of isocline.
It's like a phase diagram, just a line or a line over which like all the values.
Yeah, if right, I mean, yeah. So basically, yeah, wherever they're all pointing in the same direction, that's sort of like that they all have the same phase, right? So yeah, you could sort of look at it that way. This is just, I think in this figure, they're just showing that, if you had a map, this must be I think this is someplace in the Netherlands or someplace, lots of houses, then obviously this image would be very well represented by a Fourier Transform component like that. Yeah, that would be one of your main components. Just to get sort of a better sense of how to think about K-space. So a very important part of K-space is the center K-space, Kx equals 0, Ky equals 0. And from the point of view of the phasors, that's where all the phasors are lined up. Okay, they're all pointing in the same direction, and that's typically what we assume happens once you've excited the magnetization with the RF pulse, and you assume it's very short, then at that point you start off with everything lined up. So you start off at the center of K-space. And then you apply some gradients. In this case, Kx is still equal to 0, because if you go across any row, the spins have the same phase, right? So that's how you can tell Kx equals 0. But if you go across y, the spins vary in phase. So you know that Ky must be different from 0. Right? So this Fourier component is Kx equals 0, with Ky has some value that's causing this very late variation of the phases in the y direction. Okay, so let's take a look at some simple examples. So here's Kx equals 0, Ky equals 0. So that's pretty simple. They're all pointing in the same direction. Here's Kx equals 0.25, Ky equals 0.5. So let's see if that makes sense. And these are all representing e to the minus j 2 pi kxx plus ky y. Okay, because you always have to define what you're plotting, because there's a sign. You have to say, is it plus or minus, phase. So let's look at this. So here, Kx equals 0.25. That means the period is 1 over 0.25, right? So I should expect to see a period of 4, right? And in fact, I see if I pick any row, right? If I go from here, I have to go all the way from -2 to 2 to get the same phase again. So that makes sense. The period is 4. Okay. Similarly, Ky equals 0.5. That must mean the period is 2, right? So if I go along any column now, I say, okay, well, I have to go 2 steps before the phasor pattern goes back to the same phase. So that makes sense. The period is 2. Okay, now let's think about the sign. This e to the minus j 2 pi kxx means that as I move along the x direction, I'm going to go clockwise, right? Because I'm going to have negative phase, right? So because this kx is 0.25. So that's true. As I move along this way, you sort of see the phasors are going clockwise. From here to here is a 90-degree clockwise rotation. Same thing if I go Ky equals 0.5 means if I move 1 step, I'm going to go clockwise here. But since here I'm moving in steps that the phases are going by steps of 180, I can't really tell, right? So this could be plus or minus 0.5 given this diagram. So it's ambiguous, right? Because you can't tell 180 from minus 180. So if you ever see that, then you just say it's ambiguous. Now here, we've kept Ky equals 0.5, but now Kx equals minus 0.25. And so you sort of see here, as I go from here to here, it's moving counterclockwise, right? And then here, I've kept Kx equal 0.25, so it's moving clockwise here. And then here, just want to point out that along any row, there's no variation in the spins. And so therefore, I must be at Ky equals 0, right? I'm at 0 spatial frequency in the y direction. So this is basically the basics of how to interpret where you are in K-space just by looking at these phasor diagrams. Whoops, I guess I have to make that. Okay, so let's just recap again. Where we're headed is we want to get to the Fourier transform. So let's just recap what the Fourier transform does. It means if I want the Fourier transfer of some function gxy, then I have to take that function and I have to multiply it by this complex phasor term, right? And then after I do that multiplication over all of x and y, then I need to integrate over all of x and y. Okay. So this multiplication step, you can consider that's the encoding step, right? That's what the gradients do. They impose this phasor pattern on my object. Right? And then the receive coils then do the integration. All right? So this is encoding, and that's integration. Okay. So what that means is, for example, let's say, and here we'll start with a simple example. Let's say I want to calculate the value of the Fourier transform at this location along the kx axis. I just want to calculate what that is. Well, what the formula says, and here I'll use just a big integral just to say I'm summing over space. I'm not just to keep the notation simple. So this is a integration over volume. Okay. So it means I take my object and I multiply by something that has variations that vary along the x direction. And then this tells me sort of how much of my object can be represented by the spatial variation. And then I put that number and I plot it here. All right, and so that's the value of the Fourier transform at that location. Similarly, if I want to figure out what's the value here along the kx axis, and I take my object, I multiply it by the this sort of spatial variation. You can sort of see I'm a little farther out here than I was here, right? So this is a finer spatial variation, smaller period, but the same thing. I multiply and then I integrate and I get this. Okay. If we look at the same thing with phasors, if we were doing this mathematically, we would take my object, I multiply by this phasor pattern, and you can sort of see this has variations in x, but no variation on y. And I do this, and this is what this gives. Okay, so that's actually the calculation we do. This is sort of just a very simple way of looking at it, but in reality, we use complex phasors, right, in the equation. Right, this is the complex phasor pattern. So that's what we do mathematically. Now, the integration, the multiplication here in MR is done implicitly, right? Because that's just the value of how many protons you have. And so basically, if I have 0 protons at a location, it doesn't matter what the phase is, right? There's no contribution. So that multiplication is just inherent to the process because you're imposing the spatial encoding on your object. Where there is no object, then it essentially gets multiplied by 0. Where there's a lot of object, then you're going to have a lot of spins right at that phase, and so that's how the multiplication gets done. So the really cool thing about MR is it's doing all this stuff in the physical world. It's doing encoding, it's doing multiplication, and then you're doing integration. Right. Similarly, here at this point along the ky axis, you have a spatial pattern. So notice this varies along the y direction, but does not vary along the x direction. You do this multiplication, you sum it up, and then you plop your value in there. So every value of k space, you can imagine, it's basically taking your object, comparing it to some spatial pattern, and then saying, okay, if there is a component of my object that could be represented by this spatial component, I should have a pretty large value. And if there's no component, if my object looks nothing like this Fourier component, then I should have a very small value. And maybe I should have 0 in some cases. Okay, so integration is a really important point. So we're going to hammer on that a little bit in terms of this process of encoding and then multiplication and then spatial integration. It's sometimes a little hard to get around, so we're going to take a few stabs at it. So here is a thought experiment. So here we have the object is obviously let's assume it's some uniform object. That's the shape of, let's say, a bar of chocolate. Okay. And we put it in an MR scanner, and at one point in time, we've got this spatial pattern of the phases. Okay. And you can sort of see that this is sort of a diagonal spatial component, right? You're sort of seeing these lines of constant phase, of equal phase, being diagonal, right? And then what it's saying is now sum up all the spins in that volume. That's integration, right? And if I do that, I would get this arrow here. So, and then that's a complex number, and I would take that complex number, the real and imaginary part, just put it in to someplace in K space. So for example, here in K space, you know, I'm out here, right? So this value would just be put into that part of K space. Right? The key is that it's not it looks like a fairly small arrow, right? I mean, things canceled out. So for example, you know, because it's uniform, you know, this spin cancels out the contribution of this spin. For every spin, you can find another spin that's sort of equal and opposite, you know, because I've got sort of all these uniform, these variations here, and the object is uniform. Okay. So it sort of makes sense that a lot of things cancel out. So we're not going to get a very big value here. But now let's consider changing my object. Okay, so I'm going to take that bar of chocolate, and I'm going to imagine like cutting diagonal stripes out of it, right? So I'm going to actually make my object look more like my Fourier component. Okay? So that's shown here, right? So all these here, these are all 0 now, right? Because I just removed the chocolate, right, from those parts. And so that not having spins there is sort of essentially like multiplying by 0, right? So my object is 0 here, and it's got a value here. And now when you think about it, when we add up all these components, I get a really big value for my Fourier component, okay? Because now my object matches my Fourier component. Okay. Does everyone see that? So once again, let's say my object is this bar of chocolate, but it's got zeros all in these regions. Right? I impose a spatial pattern. The spatial pattern is this, right? But because it's 0 here, I essentially get rid of these spins, right? And so now this spin here, there's really not, previously this guy was canceled out by like this spin here, but this spin's no longer here, right? So therefore, when I add everything up, we get this constructive addition, and I get a much bigger value for my Fourier transform. So that's got basically, you've got encoding, you've got multiplication, and you've got integration all right there. Okay, and so without going into too much detail, as we said before, the integration is done by the receive coils. And so, for example, if you have a body coil, you know, it's essentially going to receive the contributions of all the spins in its sensitive volume. Okay, and so the value you get, without going into too much detail, you can sort of just say it's integrating that. Now, in reality, you're not going to have a uniform reception. So you might have to, you know, if you really want to be precise, you have to take into account the coil sensitivity. But for this course, we'll sort of assume things are uniform until we get to parallel imaging, in which case we'll look at when things are not uniform and how we can actually leverage that to go even faster. Okay, so to recap, this is the recipe, the MR recipe for the 2D Fourier transform. So the amazing thing is that we're going to take this mathematical expression and implement it in the real world using the spins. So assume I'm at some location in K space, Kx, Ky. First thing I have to do is create that spatially varying Phasor pattern, right? That's with the gradients. Okay. The next thing this formula is saying, I'm going to multiply that Phasor pattern by my object to get the gxy times this thing. But as we said, that in MR, that's basically implicit because that's just how many spins are at that location, right? If there's no spins, then I'm essentially multiplying 0. If there's a lot of spins, I'm essentially multiplying by a big number. So that part is essentially for free. And then I integrate over all those, all of space. Okay, so that's one key is to get one point in K space, I have to integrate over all of image space or all of object space. Okay, and that gives you one point in K space, right? And so that's basically the integration step. Okay. All right, so let's take a look. This is a movie. I think it's in. I've also posted the movie onto Canvas. So what you're going to see here, this is the object. So basically it's 0 here and it's 1 here. And this is going to be the spatial Phasor pattern that's imposed. And this is what happens after I multiply this spatial Phasor pattern by my object. So basically it's zeros here, and then only the spatial pattern lasts here. And then this is going to be the complex sum of all these Phasor patterns. Okay, so we're going to go through this movie, and we're going to watch how things go. We'll go through it quickly first, and then sort of step through it more slowly later. So you can sort of see here, I don't know if you can see that, but it's hard to tell. Right now we're at the center of K-space, all the spins are aligned in the same direction. Okay. If you download the movie and look at it there, hopefully it'll be a slightly better resolution. But because there is summation, because all here, all these things can sum up, right? All these things can sum up, and there's nothing to, because everything's going in the same direction, these can all sum up, there's nothing to cancel out. So we get a pretty big value here, right? Because half the image is uniform, right? Let me just play through the image, so you sort of see that that's going, and then we'll step through it more slowly. Okay. So you sort of, if you notice this stuff, you look at the phasor pattern. Okay. So let's step that through a little more slowly now. Okay, so we start imposing. You sort of start seeing how we're moving along the ky axis because you're starting to see variation in the y direction, right? And you notice that, for example, when that variation is at a certain frequency, the vector sum can be very small, right? Because here we've got vectors pointing in opposite directions, and so things cancel out. Okay. So like if this spatial pattern here, right, I get very little Fourier component because this spatial pattern it's not really a good match for my object, right? So then if I think about summing up all these spins, it's basically things are gonna cancel out. Right, so for a lot of these, you sort of see this, the spatial pattern is just not a very good match for my object. Okay. So let's scroll along here until where it sort of gets big again. So that's pretty big here, okay? And so you sort of see here, I've got this, if you look here, this pattern, you can sort of see the key point is sort of like varying here, here, here. So this spatial pattern is a relatively good match for my object, right? So I'm gonna get a relatively large value for my Fourier component there. Okay. So you can play around with this movie at your own pace if you download it. So let's do some examples, and then we're going to split off and do a in-class exercise, and we'll do breakout rooms online and see how that works out today. Okay, so here's the idea. We take this phasor pattern and we multiply by our object. Okay, and so we think about the vector sum of everything that survives. That means we just add these all up and we get 25. So that's the vector sum. Okay. So this is at kx equals 0, ky equals 0, because the phasor pattern is all pointing in the same direction, right? Now let's say we have the same phasor pattern and we want to pose it on this object here. Okay. So now all of a sudden things are a little different. This is a sort of weird object because it's like -1, 1, 1, 1, -1, -1, 1, 1. So in this case, anywhere there's a -1, let me change my color here. So I get maybe good color here. The orange is best. Okay, so basically what I'm going to do is wherever it's multiplied by 0, I don't have to worry about that because anywhere it's 0, it's not going to add up to the sum, right? So I don't have to worry about where it's non-zero. So basically I'm going to have all these guys are multiplied by 1, so they keep pointing in the same direction. And the ones that multiply by -1 go in the opposite direction. Okay. And so therefore, if I add all this stuff, it's going to give me -1. Okay. And that's because this phasor pattern is not really a good match for this diagonal object, right? Here, if I go out to this component here, right? Let's see. Whoops. Sorry about that. So here I've got something that looks like it's got diagonal variations, right? So here, these are all the same phase, these are all the same phase, these are all the same phase. So now if I do this, you know, I get this variation of the spins. Right? Yeah. So after multiplication, all the spins line up, and so I get -13. And similarly, if I have this object here where everything is 1s, and I multiply this, then all these add up constructively and I get 13. Okay. So that's shown by these movies here. So for example, here we're going to have, if I have this object, then the vector sum is pretty strong. Right? Whereas if I have this object here where all these are 0, then at the when I'm at kx equals 0, ky equals 0, I still add up the spins, and so I get here the sum is 13, but it's not as high as this one, which is 25, right? Because here we have all the spins that add up together to give me my vector sum. Okay, so we're going to do an experiment today. This is the first time we're doing a hybrid. So what I'd like you to do is this. I'm going to explain. We're going to take about 10 minutes to do this in class exercise. So here's the problem. For each of, this is your object here. It's a very simple object. It's 1, 0, 1. It's just 1 along where it's orange and 0 everywhere else. Okay. And then each of these parts represents a certain part in K space. Okay. And then what you're asked to do is we'll do A together, and then you guys are going to do B, C, D, and E on your own in small groups. And so the idea is that for each part of these, you have to tell me where you are in K space and also what's the vector sum. All right. And we'll use the chat feature, so you can just enter your answer to the chat. You know, if you work with someone else, just put your name in and just write down your answers. And same thing with the breakout rooms. Okay, so let's look at this place here. For A, all the spins are aligned, right? So there's no variation either in the x direction or in the y direction. So for this one, we would say kx equals 0, ky equals 0, right? And the vector sum is just 5, right? Because these things here get multiplied by 0, so these don't contribute. So it's just 1 plus 1 plus 1 plus 1 plus 1, and that's the vector sum. Right? So go ahead and for the next, say, 10 minutes or so, you guys, if you're in the room, go ahead and assemble into small groups. It doesn't matter the size of the group, 2 or 3 is probably optimal for social distancing. What I'll do online is I'll break you into, let's see, there'll be 4 breakout rooms online. Okay. Any questions before we start this? Okay, so if you're in class, go ahead and start talking to your neighbors.
Professor, before you break out, I think we should make a screenshot, because when we get in our room, we will not be able to see the question.
Okay, it's so go ahead and take a screenshot, or else it's also in the PDF that's on Canvas.
Oh yeah, okay, thank you.
Okay, all right. So I'm gonna send you to breakout rooms now. We'll get you back in about 10 minutes. Let's see if I do that. Breakout rooms. Okay, I'm sending you now.
So this so it's the same as yeah. Yes. So this one is they're both
Hello? Hello?
Okay, so is there a question, Dawei, had a
Yes. So I'm a little curious. So what is what's the number like under kx and ky? What does that? What was that again?
It's the vector sum.
Got it. Vector sum.
Yeah.
And then, so basically the answer format will first have the vector sum and then kx and ky.
Yeah. So go ahead and if people can start as you're finishing up, just enter your answers. Let me.
Got it. One moment.
So you're in class. Just each group, if you just post your answers to the chat. You can do it everyone or directly to me. It doesn't matter. It's just more for me to get a sense of where people are. It's not, we're not recording anything or anything like that. Okay. Okay, we'll wait for everyone to rejoin online. It seems like everyone's rejoined. Okay, so let's take a look at this. Doesn't look like anyone's posted, so we'll just cold call people in the room and online. How about for B? So where are we in case?
Excuse me. So for the link you provided, it seems to be saying waiting for the BE280A's presentation to
Yeah,
begin.
sorry, ignore this thing. Just enter it in the Zoom chat.
Got it.
Yeah. Any questions? Okay, so let's just, this is an experiment. It's the first time doing hybrid, so sorry about the hiccups. So let's just work through this. B, so where are we in K-space on B? So let's, where are we in KY? Anyone, where are we in KY? 0, yeah, okay, good. Right, because there's no variation along the Y, right? Okay, what's the spatial period along the X direction? What's the spatial period? How long? Go ahead. 2, right? Spatial period is 2, so kx must be 1/2, right? And then the simplest thing is what's the vector sum?
Excuse me, Professor.
Yes.
I have a question for the kx.
Yeah.
I'm confused, like why it is not -1/2?
Oh, that's a good question. It could be -1/2, right? So either 1/2 or -1/2 is an acceptable answer. And why is that?
Okay, thank you.
Because we can't tell whether it went 180 positive or negative, right? So that's the ambiguity. So we could say or -1/2. Okay. And the vector sum there is pretty easy. It's just what, -4 + 1, which is what, -3, right? Okay, great. So everyone okay with that example? Okay. So these are really simple examples. You're going to have a harder example on your homework. So if you have any questions now's the time to ask. All right. Okay. C. Where are we in K space? Where are we in KX? Yeah, no variation along X. What about KY? 0.5 plus or minus 0.5, right? Okay. And what's the vector sum there? Once again, -3, right? Okay. All right, how about D? Where are we in K space here? Once again, 0.5, right? And KY is the same thing, right? And what's the vector sum here? Yeah. That's pretty big, right? Because it's the largest we've had so far. You can sort of see how that spatial pattern is matching my object pretty well, right? Okay, and the last one, where are we in K space with KX? And now we can tell the sign, right? 0.25, right? And it's positive 0.25, clockwise rotation. And if we're looking at, if we're assuming we're having e to the minus j 2 pi kx, we know as we go in the x direction, it's the negative phase, right? For a positive kx, right? And what about ky? Yeah, good. And the vector sum here is, what is it? 1, right? Because the plus j and the minus j's cancel out, so we're over. Now it could be that you can have complex answers to the Fourier transform. You can have complex values, okay? So that's okay if you do end up with complex values. All right, great. Any questions on this example before we move forward?
Professor, do you mind doing kx is equal to -0.25 and ky is equal to 0?
Yes. So basically, yeah. So basically, the what's shown is kx equals plus 0.25, right? So
Yeah.
if you had negative 0.25, then it would just go in the opposite direction. Yeah.
Do we still have to turn in the answer anywhere?
No, don't worry about it. It's more just, this is more just, just to sort of get people thinking about this so that you can ask questions here while we're in the room. We're on Zoom. All right. So yeah, so if you're having trouble with the homework, that will be posted later today, I guess. So homework probably posted. There will be something that's got a much bigger object and more complicated patterns. And so, but if you understand this example, just work through it and take the, take these principles and apply to that problem. All right. Okay, if there's no more questions, let's move on and try to finish up the subject material for today. So we're gonna sort of, the next part is actually just, we're gonna walk you through some of the mathematics just so you have it and sort of understand, how we think about this with sort of mathematical notation. Now we're gonna start, saying, okay, my b's of z is a function of x, y, z, and it's going to be b0 plus gxx plus gyy plus gzz. Okay, and gx is just dbz dx, gy is just dbz dy, and gz is just dbz dz. And we talked about what those look like before. Okay. We're also going to now start defining things. We're going to define a gradient vector that's going to have gx, x, gy, and gz as its components. Okay. And we'll have our typical position vector here as well. And that's going to be useful because then we could use the dot product of g dot r to get me gxx plus gyy plus gzz. So I'm essentially adding up all those gradient terms just with that notation. And so that means that I can say that in any location r as a function of t, my gradient, my magnetic field in the z direction is just going to be b0, my uniform field, plus g. And we're going to see later on that we're going to make a really critical part of MR is that the gradients are not static. We turn them on and off. Okay, oftentimes very quickly. Okay, and then if we take the dot product of g dot r, then that gives me this which tells me how much what this all adds up to give me my delta b. Because all those gradient terms, every gradient term, gx, x, gy, gzz, they all have a little contribution to delta b, and so I have to add them all up to say what is the actual field I have at the location. This is just review. This is just to remind you that previously the solution we got was that we have a time varying phasor that just rotates at omega naught. We said there's a clockwise rotation at omega naught. All right. Now we're going to modify that to look at what happens with the gradients. Okay. So remember, the longer frequency at every location is just gamma times the local field, B sub z. Okay. So now we can have gamma B naught. That's the omega naught term we've been dealing with. And then we're going to define this delta omega. Okay, so that's like the incremental frequency reference to the isocenter. So very similar to the first problem we did. At isocenter, we're always at omega naught. As we move away from isocenter, we're going to have either delta omega can be either positive, which means it's going at a faster frequency, or negative, which means it's going at a lower frequency. Okay, and that's delta omega just given by gamma g dot r, and this is a function of both space and time. So now we want to take that frequency difference and go into phase. Okay, because remember the example we've done so far, we're looking at sort of the phase pattern. Okay, and so the thing to remember about MR as you go through the MR experiment, essentially every part in K space is a different phasor pattern. Okay, so to get all the points in Fourier domain, you've got to impose different phasor patterns. So you impose this phasor pattern, calculate the Fourier transform, impose another phasor pattern, calculate the Fourier transform. You go on and on and on until you've collected enough points in Fourier space where you think, okay, now I have enough points that I can reconstruct my image. All right. So what that means is what we really need is we have things in terms of frequency, but now we need to convert that into phase. And phase as a function of location, because that's what really matters for the Fourier transform, right? It's the phase at every location that comes into that complex phasor pattern. So this is how we do it. We go back and realize, okay, well, the change in phase is proportional to my frequency. Okay, so that means I should just be able to get my phase term and this negative is because we're talking about clockwise rotation. Okay. So that means if d phi dt equals minus omega t, then I can just get my phase at any point in time by just integrating this up to that point in time. Okay, so that's given by this. I take from 0 to t, I just integrate my omega term, and I'm going to have a omega naught t term. We've already seen that. That's the clockwise rotation. And then I'm going to have this delta phi term. And this is the term that we're going to focus on for the rest of the lecture. Okay. This delta phi is given by negative of the integral of this delta omega term. Right? So how different your frequency was from isocenter, you're going to integrate that over time. And that turns out to be just gamma times g dot r. And you notice this is integrated over t. So this is going to be the area of my gradient. Okay, if I have my gradient varying as a function of time, it just says where my phase is just going to be the integral of that gradient over time. And that's going to be the key insight we need to have. Okay, so let's take a sort of look at what happens with the gradient. So imagine here you're at isocenter, right? So at isocenter, remember the spin just stays at 0 phase, right? It has no additional frequency, so it's just going to stay there. That's in the ideal case, right? Now we turn on the gradient here, and so this spin will assume is not at isocenter, so it's going to experience some net phase. And so over the course of time, it's a positive gradient. So, and assuming it's a positive x location, it's going to acquire this phase, and you sort of see it's like 45 degree clockwise, 90 degree clockwise. What is that? 135 degree clockwise, right? So that phase is just given by minus gamma gx x times where you are in time. So here we're at time t1, we're at another time t sub 2, and here we're at another time t sub 3. So in the presence of a constant gradient, that phase just increases linearly, which is what we expect. And so you can sort of tell that this phase term is just the integral. We're just integrating this gradient, okay, over time. And since it's constant, that integral is just gx times the time. In this case, t sub 3 or t sub 2 or t sub 1. Now, the interesting thing about MR is the spins actually, as we said before, they do exactly what you tell them to do. So they actually have a memory. So for example, if I come along with the same spin and I give it a gradient, and then it's at some phase here, say 45 degrees, negative 45 degrees. But now I turn off my gradient. I say, okay, you're going to go back to the isocenter in terms of frequency. You're not going to be offset frequency anymore. And I come back and look, this spin keeps the phase. So it remembers where it was, okay? And if you think about, if I integrate from here to here, that's the same as the integral from here to here, right? Because this is 0, integrating over 0 doesn't add any more phase. So if I turn off the gradient, then I'm not accumulating any phase due to that gradient. So the spin basically remembers where it was. And now the interesting thing is now I turn on the gradient here, and it starts off from where it was because it remembered its phase, and then just adds on an additional phase term here. And so that where it is phase here is just the integral related to the integral of this gradient here. Okay, and this part here didn't really contribute because it was 0. So what we end up with then is the transfer of magnetization, if we think about it, is going to be whatever magnetization there is, that's related to how many spins there are in a certain location. We're going to have the T2 term that we talked about, and we're going to have this phase term. That phase term has that e to the minus j omega naught term we've talked about, and then it's got this exponential of this delta phi term. Okay. So this is basically what's going to tell me what my phase is as a function of space and time. And so typically we have to integrate over a whole volume. So we have to integrate over dx, dy, dz. And if we do that, we're essentially doing like, we can sort of, we're getting the volume, all the spins from the whole volume. And to do that, there's the x, y, and z components. So we typically have to talk about a 3D Fourier transform. Okay. But to keep things simple, and also it has advantages for certain types of imaging, we might be interested in just looking at the image from a single slice. Okay. And so we'll see later in the class that it's actually possible, if let's say I had a volume like this, okay, instead of looking at all the spins, what I can do is I can excite a fairly small section of spins with delta z, and only those spins are going to contribute to my image. So that's a pretty cool trick. We'll see later how it's done. But just assume for now, there is a way in MR to just excite the spins in a certain slice. Okay. And then therefore, we're just going to look at a 2D Fourier transform of that slice. Okay. So we're going to integrate over that slice such that we don't really care about variations within that slice. We're just assume that we don't care about that. And so then we're just left with a 2D Fourier transform. So mxy is just the integral of the volume along some slice delta z. And we go through the math, we find it's equal to our signal that we get out is mxy e to the minus j omega naught t times this term here. Okay. This is our delta phase term here. Okay. We're still left with this e to the minus j omega naught t term. So it turns out that we can mathematically get rid of that. We just do what's called demodulation. Those of you who are double Ds know all about that. We can just do a complex demodulation, get rid of that term. And so we're just left with this. So let's expand this out. We've got our object. We've got this sort of phase term that we've been dragging around and using this compact notation. Now we're going to expand this back and say, well, that's just gx, x, and gy, y. Okay. And then we can look at the integral, this integral over t. Okay. So what we can do is we can sort of evaluate those. The x is not a function of t, so we can sort of pull that out. And so for each of these, we can end up with writing this as this is just equal to the object e to the minus j2 pi kx of tx plus ky of ty, where kx is gamma over 2 pi, the area of my gradient, and ky of t is equal to gamma 2 pi, the area of my y gradient. Okay. So this is pretty remarkable. It just says that if I turn on my gradients, okay, I use this formula to tell where I am in k-space. Okay, where this says, if you want to know where you are in k-space due to the gradients, this formula tells you, okay, you're at this point just by integrating the gradient area or defining the gradient area. And then what it means is that if the gradients have moved you to this point in k-space, at that moment, if you look at the MR signal, then it's going to give you the Fourier transform at that location in k-space. So we use in MR, we use the gradients to move around in k-space. And at every point in k-space, we look at the signal value, and then we record that and say, okay, well, this is the value of my Fourier transform at this point in k-space. Okay, I'll use the gradients to move to another location. Okay, now I get another value, and so on and so forth. Okay. So one of the key engineering challenges in MR, or questions in MR, is how do you go through k-space? What's the best way to go through k-space? And how much of k-space do you need? So we'll get to some of those questions as we proceed with the course. The key is that the MR signal is essentially now the Fourier transform. So at every time point, you're getting a value of the Fourier transform at some location, kx of t, ky of t. I think I'll just skip over this. This sort of sums it up. And this is also just a summary slide. So the key is the gradients control our position in k-space. And when we design sequences, we're always trying to figure out how efficiently can we move through k-space. Okay, so let's take a look at a very simple k-space trajectory. So here I have gx of t. I turn it on time equals 0, and I keep it on till time t sub 2. Right? And that just means that in k-space, I'm just going to be moving out along the kx axis. All right? Because you imagine integrating this function, calculating kx of t equals gamma 2 pi, the integral of that function up to some time t. And so that's just going to be, if I think about integrating this, the area just gets bigger as I march along time, right? And that for this line here is just going to move like that. Okay. What it means in terms of phase is, notice here, I start off at kx equals 0, and then I start making the spins get out of phase. So here, this is half a period, right? And now here, I'm at a full, this is a period, right? So this is a low frequency, a higher frequency. So because I'm moving out in k-space. Let's talk a little bit about units. Gradient strengths typically have units of gamma, Gauss per centimeter, or millitesla per meter. So typically, for example, GE in the United States uses Gauss per centimeter. If you're dealing with a system from Europe, for example, from Siemens, it'll be in millitesla per meter. But they're pretty good about sticking with SI units, whereas in the US, we sort of use whatever we feel like. Okay. Gamma over 2 pi, remember, has units of Hertz per Gauss or Hertz per Tesla. So if you sort of multiply all the units out, you end up with kx has units of 1 over centimeters, which makes sense, right? Spatial frequency is 1 over the spatial period, right? So now let's sort of plug in some formulas. This is the typical, this is what we just did. Now we're just plugging some values. Gx equals 1 Gauss per centimeter. Okay. So I have my gamma over 2 pi. Let's say I wait to t sub 2 equals 0.235 milliseconds. So now I take that 4257 Hertz per Gauss. My gradient is 1 Gauss per centimeter. And I multiply by this time, 0.235 times 10⁻³ and I get 1 inverse centimeter. Okay. That means if I apply this gradient on and I look at it at time t sub 2, this spatial pattern, this period is 1 centimeter. Okay. So that means, and this 1 Gauss per centimeter is a very, that is in the range of what's used on clinical systems. So that means that if I put you in the scanner and I apply a gradient, 1 Gauss per centimeter, and I look back after 0.235 milliseconds, then if I look at the spins in your body along the x direction, within 1 centimeter, the spins would have repeated their pattern. Okay, every centimeter, they're going to repeat their pattern. So that's what that means. Now remember, the spins have memory, and so we can turn off gradients and turn them off, and we can sort of have a lot of freedom in doing that. So for example, look, this is a very simple k-space trajectory. Gx of t, we turn it on. So during this period, we're only imposing variations in the x direction, right? So in this period, we're moving along the kx axis, right? Then here, we turn off the gradient, right? So we're not going to accumulate any further variation in the x direction. It's going to memorize the spatial pattern, but it's not going to change the spatial pattern in the x direction anymore. So therefore, we're not going to move out any further along the kx axis. But now we turn on the gy gradient, and so now we're going to impose spatial variations in the y direction. Okay? And the longer we keep that on, the further out we move in k-space. Okay? So we've actually gone from here to here. and it's taken us this whole time. Okay. But let's say you're like, well, I don't really have time to wait. I'd rather just go from here to here directly. So how might you do that? What would be the obvious solution? Go ahead. Yeah, just apply it at the same time. Yeah. Which, is there a slide on that? If not, there should be. Maybe there's one later. Okay. So let's walk through this example here. So now we're starting to look at pulse sequences. So this is an RF pulse, which we'll talk about later. But you'll notice it's a sync pulse. I'm going to turn on the GY gradient, and then we're going to turn on the GX gradient. So sort of opposite to that example we just did. So we're moving along KY first, and then KX. And so let's just look at the spatial patterns to sort of incorporate that. So here at location 2, I'm going to fill in this part in K space, right? And so you sort of see here this spatial pattern. If you zoom on it, this is one spatial period from here to here. Okay, so the things are changing along the X direction, the Y direction, and they get back to one period over that. Okay. Now I leave the gradient on for longer, so I'm here at this location. So I've moved out to here, and so I'm going to fill in this part of K space. Okay, and now you see this, the phasor pattern has a smaller period because we're at a higher spatial frequency. Okay. And now I don't move out any farther. So now I'm at this point here. So I turn off the Y gradient, I turn on the GX gradient. Now I keep the variation in the Y direction, right? Because I've already applied that, and the spins will remember that. Now I apply variation in the X direction. And so what that's going to do is it's going to keep the variation in the Y and add variation in the X. Now I'm going to have a diagonal pattern. And that's shown here. And I'm going to fill in this part of K space now. Okay. That's a very simple example of how we move through K space. Here's sort of a movie of what that looks like in sort of finer resolution. I'm imposing variations in the Y direction. And now I start imposing variations in the, let's see, oh, yeah, now it's the X direction is coming in. Okay. So let's play that one more time. So you watch as the variation is going to, the frequency is going to increase in the Y direction first. Okay. So we get to a fairly high spatial frequency. And then at some point, we're going to stop that, keep that in place, and now starting adding variations in the Y direction. And the more variations we add in the Y direction, the more that diagonal becomes tilted. Okay, so here's the slide. So this was your suggestion. Yeah, if you don't want to wait, just you can apply both variants at the same time, and that's fine. Okay. Now, in practice, there's limits in terms of what you can do, but for this, you typically will play. If you can play gradient at the same time, you do because it saves time. We'll have to do this on Monday. So let me just give you a sort of preview. We have 1 minute, so at least we can give you a sense of where we're going, and then we'll at least you'll leave today knowing sort of how basic pulse sequence works. So essentially, the idea is we want to just acquire lines in K space. The simplest thing is just acquire line after line after line after line, right? So how do we do that? Well, the way it's being done is what's called the spin work pulse sequence. So we have these two gradients, they're negative, so they move us out to this point. And then we turn off the Y gradient and we reverse the X gradient. So now instead of moving us negative along KX, it starts to move us positive. Okay. And then we just repeat that process over and over again, acquiring lines in K space. And so you notice that the only thing varying between these is the size of this initial GY gradient. Okay. This one moves us out here in KY. This one didn't move us out as far, so we just moved to here. And this one had no gradient applied, so we stayed on the KY equals 0 axis. We just went this way and then this way. Okay. And so we repeat that process over and over again. You can sort of see how we can start sampling K space, just line by line by line by line by line by line. All right. So that's all for today. We'll pick up on that again next Monday. And so, yeah, I'll stick around here if there's any questions. Otherwise, we'll see you next Monday. Thanks.